Here is another example. We are doing it by using the controllable canonical form. Here is the given mathematical equation y double dot plus 3y dot plus 2y equal to u dot plus 4u. Now when I write it down in S domain, it's going to be s square y plus 3sy plus 2y equal to s times u plus 4u. Here in this system, y is the output, u is the input, and only one transfer function. So to simplify, to solve this, to find the state equation, output equation for this system, here I have poles. Okay, the numerator of this is nothing but represents the poles, denominator represents the 0. My apology, numerator represents zeros, denominator represents poles. It's almost 3 a.m. that could be the reason. Okay, I will do one more example and I will stop it. Anyhow, so here this is number of zeros, number of poles. As long as it has zeros, we have to divide that system into two subsystems. Okay, so what I did, I derived another function or another term, z. Okay, so y over z, z over u, it's not equal to. So basically what I'm saying, y over z, z get cancelled out, it's going to be y over u. I'm going to take this as a system 1, that's as system 2. I'm representing system with h. Okay, so now basically what I'm doing here, system 1, that h1, how did I define? Let me go with the h2. Basically this must be h2, this must be h1 though. Okay, because I have this as z over u. Okay, now I define z over u equal to 1 over s square plus 3s plus 2. So okay, so system 2 equal to here is my system 2, z over u, 1 over s square plus 3s plus 2. So basically when I write this in this format, z double dot plus 3z dot 2z equal to u. Okay, so z double dot equal to, I'm going to rearrange the terms here. So it's a second order system, so basically two integrals. Okay, and my output is z instead of y. Okay, now how do I get z double dot? So z double dot, I get the u minus, so if that is z, this must be z dot, this must be z double dot. Okay, to get z double dot, u, so that's a plus, minus 3z dot minus 3z dot and minus 2z. So I have minus. It doesn't matter where do you put your minus. I mean, if needed, you can do this as plus and you can put the minus 2. It's not going to make any difference, but it's a good way of keeping the minus there. Now I'm going to look at the first one here. So system 1, to get y, I need to get y. I have two terms, so one is z dot, so z dot, that's a positive, and 4z, so 4 times z, that's also positive. So that's how we'll end up getting y. So from here, now I'm going to take the state variables x1 dot, x2 dot. Okay, what is x1 dot? X1 dot equal to x2, and x2 dot equal to minus 3x2 minus 2x1 plus u, y equal to 4x1 plus x2. Okay, so when I write down in the matrix format, it's 0 1 minus 3 minus 2, that's a, b is 0 1, and c is 1 0 1 1, sorry 4 1, and d is 0. Let me solve one more example in this and then I'll stop this video. So here is the next example. Find, by using controllable canonical form, find the state of equation and output equation from the following mathematical function. So if you look at this, basically the number of poles and number of zeros are equal in this given function, transfer function. That transfer function is nothing but represents a system. Okay, so as usual, if there are zeros present in the system, the zeros are nothing but the numerator of the system. So there are two zeros. Then we have to divide the system into two subsystems. One is h1 of s and another one is h2 of s. So I'm going to define this as system 1. So system 1 has 1 over s square minus 6s minus 2, which is z over u. So if I write it down in time domain, it's going to be z double dot minus 6 z dot minus 2z equal to u. That's my system 1. And system 2 equal is nothing but y equal to z square minus 6z minus 3, sorry, z double dot 6z dot minus 3z. Okay, that's my system 2. Now what I'm doing, I'm going to write down draw the simulation diagram for the system 1. So it has two integrals. Okay, here is my z, here is my u. Okay, so here is z double dot, z dot, that's my z dot. Now to get z double dot, u plus 6z dot plus 2z. So I have 6z dot, that's a plus, and that's 2z. Now to get y, I have to have minus 3z. Okay, I have to have 3. Here is my y, minus 3z minus 6z dot. It doesn't matter where do you put minus, so minus 6z dot, and then z double dot. This is positive. Okay, so now I'm going to do the variables x1 dot, x2 dot. These are the state variables. So x1 dot equal to x2 and x2 dot equal to is it 2x1 plus 6x2 plus u, and y equal to what we have, 3x1 plus 6x2 plus x2 dot. Okay, so when I put the x2 dot, I need to replace that x2 dot with x1, x2 and u. So 3x1 plus 6x2 plus 2x1 plus 6x2 plus u. So I'll end up with a 5x1 plus 12x2 plus u. So when I write it down in the matrix format, A equal to 0, 1, 2, 6, B equal to 0, 1, and C equal to 5 and 12, and D equal to 1. Okay, now so far we never seen a D matrix, so here I have a D matrix. So that indicates that whenever you see D matrix, that indicates that the input and output are directly connected. Okay, so when that happens, so if something if I make any changes in the input, output must change. So probably if you see a D, basically that's a emergency case. Just like when you push the emergency button, immediately everything has to be stopped. Okay, so that's where you see this D matrix. That system will have the D matrix, the other systems won't. Okay. Anyway, I will stop it here with this example. With this, I'm done with the controllable canonical form. I'll start other two methods in the future videos. Thank you.